So in the previous lecture, we talked about the quantization of massive scalar field. This is these are the commutation relations. This is just like a generalization of a dagger equal 1, right? However, there are things to notice. In quantum field theory, look at this. What's the dimensionality of this? 1 over volume, right? We have put some frequency here. So the dimensionalities you want to be careful with, right? These operators. The other thing to notice is that Hamiltonian is an integral over all of these guys. Then we said we do normal ordering. And if you normal order, there are two sources of divergences that I went through a little bit quickly last time. IR divergence, infinite volume, and UV divergence. The IR divergence has to do with the fact that there's a Dirac delta here. So in quantum field theory, you see this relation. If you want to swap AK and AK dagger, you get spatial Dirac D of 0. Where is the infinity in there? Anyone? What is the Dirac delta function in momentum? What's the Fourier transform of Dirac delta function? Constant. That constant integrated over volume gives you infinity. That's the infrared divergence, right? And then the UV divergence, you know what it is, right? Every half of these modes will contribute. If you regulate the IR divergence by saying that, well, I'm dividing everything by volume, so that this is a fixed amount, but then you have half of that fixed amount contributing to every single K modes, and there are infinite of them. So that's a UV divergence coming from the fact that you have ultraviolet modes, arbitrary, right? So just one notation, because this, what was this? We said that this is the Lorentz invariant measure. You guys remember what it was? So this Lorentz invariant measure is nothing but the fact that you want it. You could write it as an on-shell condition. Easier. It's this guy. Right? This is integrated over all space-time momenta, but not all space-time momenta are allowed in a theory of scalar field with fixed mass. A theory of scalar field with fixed mass includes only these guys. This has a name. Does anyone know what the name of this is?
Leaps.
Sorry?
Leaps.
No. What is the name of this object in physics? Spectral density. You know, this object in physics is spectral density. So if you wanted to cook up a theory that had not one scalar field of mass m, but had two scalar fields of different masses, m1 and m2, how would you change these? You would add this term plus delta of k mu minus m2 term, theta k naught. Right? There is something you might come across with. It's called generalized free fields. Generalized free field says just put an arbitrary function here of an arbitrary function. That means what? It means the theory is still Gaussian, you'll see. That means that this means that you have a single mass mode of mass m1. This means you have two modes of mass m1 and m2. If you put an arbitrary function here, it means that you have a mass mode of arbitrary energy with a particular density given. Those are called generalized free fields. But that's just a comment for you. They're non-local. Generalized free fields doesn't have a Hamiltonian. All of that goes to hell. But you could formally define it. All right. So because this appears all over the place, oh, sorry. We were talking about the theory of single mass thing. Because this appears all over the place, and we're doing canonical quantization. We said this form, this Lorentz invariant measure. I'm just gonna write it this way. All right. This is Shrednicki's notation. So every time you see this is some covariant interval. Good. Okay. So what is the UV divergence all about? So there was a V of space that I could use to regulate the infrared divergence, but the UV comes from the fact that there is an integral over k that diverges, and I said you've been often introduce a regulator. You could pick a sharp momentum regulator, but cutting the integral at some large value lambda or capital large lambda. You observe, so in the part 2 of the course, we're going to see that depending on the theory, so every theory needs to be regulated. But depending on the theory, there are different choices of regulator we might have to use. Does anyone have a guess as why? What are the principles of quantum field theory? That's repeated many times. Locality, symmetry, right? Positive energy. So what goes to hell? What could go to hell if you just pick an arbitrary thing? Symmetry. You have to pick a regulator that respects your symmetry. That's going to be very important in different theories, right? Anyway, so here's a regulator that we pick. In this case, the theory is so simple, it's not violating any symmetries. What are the symmetries that you have for a scalar, massive scalar field? There's only, I only know of one symmetry. You know what it is? I guess. Sorry? Well, those are space-time symmetries. It's a Lorentz invariant theory. Internal symmetry, Z2, phi going to minus phi. It's a Z2 symmetry. That's the only symmetry it has, and this respects it. Okay. But the point is that this divergence goes with the space-time dimension. Good. We said that there is a new principle for quantum field theory. It says that quantum field theory always is defined using a cutoff regulator, and the physical quantities must be independent of the cutoff regulator. We have theories called effective field theories. These are QFTs defined with a cutoff, and there's a natural UV cutoff, and IR observables are independent of the cutoff, which is a repetition of what I just said. Well, let me forget about that. All right. We also, at the end of the previous lecture, we talked about this Z2 symmetry of the complex scalar field, which is phi going to phi dagger. There's a charge operator that does this. Recall in the quantization of A, the complex scalar field, how did I expand it? There was this, right? There was, I said there were A particles. I actually don't remember how I defined things, but I'm going to define it in one way. This is how I wrote. Up to a bunch of constants. I might have had like 2 pi something, right? So these are the A particles. These are the, this is dagger, B particles. And both of this definition was designed such that both A particle and B particle have positive energy, but opposite charge. So charge operation swaps it. Notice that I put A here and B dagger here. If you go back to the previous lecture, that comes out of the requirement that you want both of them to have positive energy, but opposite charge. We're going to say that that was a choice in a bit. All right. So today we're going to talk about the spin statistics theorem or connection between the two. It says that integer spins should have canonical commutation relations, meaning that the commutator should be 1. Half integer spin should have canonical anti-commutation relations, CCR and CAR algebras. This is the anti-commutator. And once we settle that, we're going to quantize the Dirac spinner. So hopefully it's clear why I'm doing that. Any questions about what we said last time or where we're going? All right. Oh, by the way, before I start, so the new lecture, the new homework is posted. And if you do feel that there is something I could do to make I don't know how useful the homework is to help you follow the lectures, but if you think that there's something you would like to see more in the homework or less in the homework, let me know. All right, because I'm designing the course here, so it could be it's important for me, this feedback. Yeah.
Who's the grader of the college?
Sorry?
Who is the grader?
What's his name? Derek Ping. Yes, Derek Ping. He's a PhD student of Martin Grudzinski. Yep. All right. So let's start with a connection between spin and statistics. A little bit of words to it. We said quantum field theory is an intrinsically multi-particle theory, right? So you absolutely have to talk about two creation operators or two particles or three particles or four particles. It's not it's part of the description of the theory. The theory will have to decide for you what happens if you have two particles. Is the wave function symmetrized or not? This is the distinction with quantum mechanics. Quantum mechanics was a single particle theory. So it was not required to make a statement about that. But QFT, the consistency of it requires to make a statement about that. A particle, we said, is an irreducible representation of the Poincare group. So what are two particles? A tensor product of two representations. And in quantum field theory, particles of this is actually a very, very deep statement. In quantum field theory, particles of the same field are indistinguishable. This is a result of quantum field. Can you see why? Because we define a particle as an irreducible representation of a Lorentz group, a Poincare group, which is labeled by mass and momentum and nothing else. Crucially, nothing else. So there is no way of saying this particle versus that particle if the mass and momentum are fixed. They must be indistinguishable. Again, another thing that is in quantum mechanics different from quantum mechanics. In quantum mechanics, there was a room for indistinguishable particles. So you could just imagine them and that, you do whatever you do. But this is a prediction of quantum field theory. You will not end up with fundamental particles of Lorentz invariant theory as being distinguished. There are, a lot of the statements I make are somewhat exaggerated at the beginning because to make a point, there are ways of defining the theory, tweaking the rules so that you have other stuff. But in the standard conventional thing that we've discussed so far, this is all you got. And this is a result. All right. So now that it makes a statement about the fact that they're indistinguishable, it better make a statement about their statistics. And then we saw that there could be, for indistinguishable particles, there could be bosons, there could be fermions. By the way, spins, bosons and spin was integer, half integer, right? And it has to do with the Z2 cover, right? In 3+1 dimensions and higher, right? In 2+1 dimension, we saw that there was the homotopy group, there was this Z cover. And a version of spin statistics tells you that you could have particles with exotic statistics. These are anyons. They can only occur in 2+1 dimensions. Quantum field theory tells you what their statistics is. It's not a choice. Quantum field theory tells you that they should have this exotic statistics. This is our hope to move towards topological quantum computers in 2+1 dimensions. That's crucial. Nothing higher. People are hoping to exploit this 2+1 dimensional representation theory statement. All right. So here's bosons and here are fermions, right? Fermions, by the way, yeah, this is anti-commutator. Do not confuse it with Poisson bracket. Although it's intimately related. Yeah, so I'll be using B and B dagger. And just to make sure everyone is on the same page. Oh no, let me first make a statement. But I'll define what the fermionic harmonic oscillator is. Just to make sure that everybody's seen that. Because your quantum mechanics course, you definitely learn about bosonic harmonic oscillator. What is a fermionic harmonic oscillator? Where's the Hilbert space? Really? Okay. I expect everybody to know this. It's a qubit. Fermion harmonic oscillator is just a qubit. Right? Why is that? There are only two states, but that comes from the fact that B dagger squared is 0. But we'll see that. Okay, it's good that I included in this then. I think I asked students before. I don't know what this word was. But... All right, so let's first go over the connection between spin and statistics. As I said, so what is spin? We had half integer spin, integer spin, and then the statement would be that half integer spin must be CCR, half integer has to be CAR, right? Canonical anti-commutation relations. And as I said, today I'm going to talk about a limited version of this, which is free scalar field must be bosonic. I'm going to prove that. And the principle, the offensive principle is going to be causality. So what is causality? There's a reason that I did not get into the details of causality in the relativist, in the non-quantum case. Because in the quantum case, I'm going to give you a very, very short definition of causality. Micro-causality, sometimes we call it. The commutator of any two observables must vanish outside of the light. Right? Why is this causality? What's the interpretation of commutator in quantum mechanics?
You can observe at the same time. Correlation.
No, it's not correlation. It is related to observables at the same time. But the commutator is a statement about affecting. You can influence something, send a message back. Signal propagation is commutation relation because you send a message and then get back a result. If you want to mess up with something in a controlled way, the commutator has to vanish, right? Sorry, should not vanish. So the commutator has to vanish outside of the light bulb, right? That is the absence of superluminal propagation of information. I absolutely encourage you guys to think deeper about this. This is a very, very deep statement that we just usually say. We don't have time to elaborate on, but we just say it in words. Okay? I want to say something about this. This is causality. Observables. I cannot stress this enough. Give me a counterexample, like a setup where I'm talking about some operators whose commutator is non-zero outside the light bulb, but they're not observables. It's already on this slide. Almost.
There are explanations indicating commutator, so it's outside of the vector. Does it get them?
No. Relativity doesn't elaborate so much.
No, even for the operators.
That's actually a pretty good example. It's a pretty good example. That's not what I meant, but that would be a good example. But I was gonna say this. Fermions. I just told you that the fermions, that it's the anti-commutator that is the big deal, right? And as a matter of fact, if you take a theory of free fermions, it's not true that the commutator vanishes outside the light bulb. Two fermions that are space-like separated at the same time, you know that the anti-commutator vanishes, right? That tells you that the commutator better not vanish, because then the 2 point, the multiplication will have to vanish. So what's the deal with fermions? A fermion operator is not an observable. Why? A simple term to explain. No, that's not the issue. Maybe derivation. Why? What is a spinner? What is the property of spinner under rotation? If you walk around by 2 pi, it picks up a negative sign. Can you observe anything in an experiment which you go around by 2 pi and doesn't come back? No, it makes no sense. It's nonsense, right? Any observable, if you rotate things by 2 pi, it should come back where it was, right? This is not an observable, right? It's a field. However, psi dagger psi at different points. This is an observer. So bilinears of the fermions is observed. Now, what I just told you, don't tell it to, like, if you tell this to a lot of physicists, they might freak out, like, because a lot of people are brainwashed by this, like, old school using the word observable and field synonymously. But literally what they just told you is true. Makes sense, right? You shouldn't be able to observe something that you go around by 2 pi and put minus sign. Right? That makes no sense.
Shouldn't it?
Huh?
Shouldn't it? I mean.
What does that mean to?
I mean, you can create a spinner like objects in.
You can create it, sure. Yeah, sure. No, there's no contradiction between that. What is that?
What did you know there is psi plus
Psi dagger.
Psi dagger, but what's the psi?
Psi is some fermion field. Yeah. Think about this. I don't have time to go through the details of this, but a fermion is not an observable. There is no way in quantum, no sense in which in quantum mechanics would observe a fermion. Come up with all sorts of your favorite design. Actually, as a matter of fact, all right, I'm not going to teach anions, but yeah, there's a beautiful story related to this and anions. Anions are, of course, not observables either, but there's a very pretty way of thinking about this. Okay. Good. All right.
We call it fermion a field.
A field. This is a field. It's a field operator. Not every field operator is observable.
But there are some.
Yeah, of course. Phi, scalar field phi is observable. Right? Okay. All observables, the commutator must vanish outside the light code. Causality. Good? So it must be the case that the bilinears of this, if you consider them as 2 pairs of bilinears and look at them outside the light cone of each other, will have to vanish. Okay. All right, so I'm going to do the proof, and this is why your answer was brilliant. So take a scalar field, and phi, this was the expansion of the field, scalar field phi. There was A and A dagger. I'm going to call this phi plus and this phi minus. For those of you guys who are a little bit more familiar with like formal theory of scalar field, this is called the, oh, oops, my signs are reversed. Sorry. This is called the negative mode. This is the positive mode. Positive frequency, negative frequency mode. So a scalar field under Lorentz transformation should transform this way. Therefore, this relation should hold for phi plus and phi minus. Now, because I want to run into a contradiction, I'm going to use a compact notation. For the commutator, I'm going to put plus. For anti-commutator, I'm going to put minus, right? So I'm going to write these expressions for plus minus. I'm going to write one line, but remember that I keep track of plus minus. Good. So let's calculate the commutator, anti-commutator, phi plus and phi minus at 2 different points. Good. What is it? Well, there are 2 of these Lorentz covariant integrals. You remember, I'm not going to write these expressions anymore. It's the commutator, anti-commutator of A and A dagger, right? And that is decided by whether it's bosonic or fermionic, right? Very good. So if I pick the bosonic case for the plus sign, I'm going to get this form. If I get the fermionic for the minus sign, I'm going to get this form, right? But if the answer to this is 1, sorry, Dirac, this is, sorry, my bad. This Dirac delta function, right? There's a sign here. This is K prime. If this is Dirac delta function, I could integrate, get rid of one of the integrals. I'm going to get this, which is the Fourier transform of which is a modified Bessel function. Hopefully you see why. You see why this is a modified Bessel function? If you are familiar with what modified Bessel function is. All right, I won't bug you. This is what it is. Importantly, the modified Bessel function, this guy does not vanish outside of the light cone. These 2 points could be space-like separated, and this is non-zero. So what did I do? I took two different possible. I'm calculating the commutator, anti-commutator of phi plus and phi minus, right? And for different choices of statistics, I find this. This is non-vanish. Good. So far, there's nothing offensive happening. This is just a calculation I've done. Now, the question is this. My scalar field, let's take it to be phi plus lambda phi minus. Lambda is either +1 or -1. Okay. Now I'm going to calculate phi lambda and phi lambda dagger at two different points. I'm going to get 1 minus lambda squared C of R. Good. I have a real scalar field. So this dagger part goes away. So this is the commutator, anti-commutator, or real scalar field is lambda 1 minus +1 CR. Good? Everybody's with me? The only, because this doesn't vanish outside the light cone, the only sensible choice is the top one. If I pick the bottom one, it would not vanish outside. All right? So this is an example that causality, the principle that forces you to make the connection, let the connection between spin and statistics is causality. This idea generalizes to higher spin. It's a more detailed proof, and I'm not going to present it here, but look up Weinberg's textbook if you're interested in knowing the proof. I think he has a proof of it there. Maybe not. I think it does. All right. So the punchline is that causality is a principle. It's a principle that we haven't quite discussed much because there was no. It was as in its current form, in its quantum form, it wasn't quite coming up. All right. Any questions? I think Peskin has this argument too. I suspect. I don't recall. It's all over the place. Every textbook has a version. Okay. Any questions? In the remaining 45 minutes, I'm going to go over, we're going to switch gears and talk about the Dirac quantization of Dirac's fermions, right? And before doing that, I just want to do, the analogy is this way. Scalar field was a collection of bosonic simple harmonic oscillators, right? Collection was, there was a bosonic mode for every K, and the bosonicness of it had to do with statistics, right? It was decided by statistics. Now, a Dirac fermion is decided by statistics that it has to be fermionic. So it becomes a collection of fermionic harmonic oscillators. So I'm going to remind you what a harmonic oscillator is. And I'm kind of surprised that this is not like textbook material. It should be. It's easier than the harmonic oscillator. Much easier. All right. So what's the bosonic harmonic oscillator? This is the action. And you recall that A dagger A is a number operator. Use the anti-commutator to write this way. This is the vacuum energy, right? 0 is a state killed by A, and the Hilbert space is constructed by the action of A dagger over 0. To normalize it, you need square root of n factorial, blah, blah, blah. Good? Familiar? All right, what's the fermionic one? The Hamiltonian is omega over 2 B dagger B minus BB dagger. Why minus? Why minus? What if you put plus? Because Hamiltonian would be constant if you would plus, right? By the anti-commutation relations. So you have to put minus so that it becomes a number operator minus half. So expect every time you're dealing with fermions, as opposed in the case of bosons, you put plus sign so that your Hamiltonian is not a number, it's something more constant. But for fermions, expect a minus sign. And you will see minus signs all over the place when you're talking about Hamiltonian Fermion. All right, that's point one. And this is a number operator. All right, so very good. As usual, as before, there is a creation annihilation operator. Vacuum is defined to be the state killed by B. One is defined to be the state created by B, but then B dagger squared is 0. Right? So the Hilbert space is two-dimensional. That's it. That's a qubit. That's all you got. Why is B squared 0? Why is B 0? What's the anti-commutator of B and B? Is 0, right? So therefore B squared has to be 0, therefore B dagger squared has to be 0. When we write the anti-commutation relations this way, it means that all the other anti-commutators are 0. So B and B anti-commute, B dagger and B dagger anti-commute, which means that B squared is 0, B dagger squared is 0, which means that Hilbert space is two-dimensional. Which also means another thing. There's a name for things that score to 0. Grossman variables. Right? So if you want to make sense of spinors and classical mechanics, you put Grossman variables. All right, that's it. This is as simple as that. There are two states, right? The energy of one of them is minus half. What's the other energy of the other one? Plus half. That's a simple harmonic. It's a qubit. Questions? Now we want to do a Dirac fermion field in 3+1 dimension. Remember that we had these Dirac matrices. This is how we constructed the representation of the Lorentz group, spinor representation. A Dirac spinor is a 4-dimensional representation with the following action, Dirac action. Remember that psi bar was psi dagger gamma naught. All right, so this is the action. Now, first, I want to say something about the Dirac field that's different. I said this before, which is different from a scalar field. I don't have time to get more into depth at this point to talk about this, but you will see the consequences of this in path integral. When we get to a path integral approach, you're going to see it. I'm just going to make a quick comment and move on. So what is that? I said this before. In the scalar field, to get a Lorentz invariant theory, you need two derivatives. Here, you can do with a single derivative, therefore you do a single derivative. Right? Because the principle was the lowest number of derivatives, lowest number of fields. So this is a Dirac action. But the single derivative means that if you write the Hamiltonian, how do you construct the Hamiltonian from the action? You start with the Lagrangian. You take derivatives with respect of the Lagrangian with respect to the field to get the canonical conjugate. In the case of a scalar field, the canonical conjugate will have phi dot. Right? Well, sorry, you take a derivative with respect to phi dot. Right? Here, because the single derivative, psi dagger, is the canonical conjugate of psi. That's very important. It has important consequences. So here's the Hamiltonian, what this looks like. I just wanted to make that comment and move on. All right, so this is a Dirac spinor. Hamiltonian could be written using the on shell as psi dagger psi dot. That's what the Hamiltonian is. So we're going to introduce these fermionic oscillators. And these are Grossman valued operators, of course, because if you remember from the representation, Lorentz representation theory of Dirac matrices, you had a pair of creation annihilation of two modes. Each of them had two dimensions, right? The left movers, right movers, and the dimensionality of each of the modes had to do with spin. These were spin half modes, right? So you have the BS, S runs from up and down. This is the spin of the mode. And then DS, which runs over up and down. And they have to satisfy these anti-commutation relations, as you would expect. Good. All right. So what is the mode expansion I'm gonna write? I can explain this equation in so many levels, but let's just do something that's closest to what we've discussed. We're gonna take our Dirac field. First, write as an integral, covariant integral. This is that covariant integral, and the remainder is for a part one momentum. Okay. All right. Of course, I have all the spins, so I'm gonna sum over the spins. There will be the BS and then d dagger of s e to ikx e to minus ikx. All right. These are the solutions. US and VS, what are they? These are the solutions to the classical Dirac equation. We solved them, right? What I'm doing is analogous, word by word, with the quantization from the last lecture of a complex scalar field. I added A and B dagger, and this is the dagger. Why A and B dagger? So that the Hamiltonian comes out as the number operator of A plus the number operator of B. If I put dagger here, the Hamiltonian would have come out as the number operator of A minus the number operator of B. So that sign is important. Similarly, same business here. This is D dagger and this is B. Now you already know by analogy, the A and B modes for the scalar, complex scalar became particle antiparticle. Here, B and D are particle antiparticles. This is another beautiful prediction of quantum field theory. So every fermion in nature, there must be an antiparticle. If there is charge symmetry, right? If there is charge symmetry. If you require that, and that's a choice. That's a choice you make. But the theory allows for them, and we see them in nature. All right. So here are these relations that I wrote. If you plug them in and calculate the anti-commutator of psi dagger and psi, here's what you find. Why psi dagger and psi? Because psi dagger is the canonical conjugate to psi. Good. So what is the Hamiltonian? Hamiltonian becomes BS dagger BS minus DS dagger. Using the anti-commutation relations, you could write this as the number operator of B particles from the number operator of D particles, and then you can take out the half out as before, right? So there will be still that vacuum divergence with the fermions. There will be the UV divergence. Is there an IR divergence? There's an IR divergence as well, right? It came from the fact that when you take the anti-commutator of the K mode and the K prime mode, there's a Dirac delta of K minus K prime. That's the IR divergence. All right, so B dagger and D dagger, they create positive energy states of opposite charge. I'm going to say charge in a second. But it's pretty clear that they create positive energy states because the numbers I'm adding them. Is this slide clear? I already told you something that maybe you didn't realize you were doing in the scalar field. If you want to quantize a theory with a set particular classical equation, so you have a classical equation of motion, what do? If the classical equations of motion are linear, that's very crucial. If they are linear, what you do is you first look at the solution to classical equation of motion. Those are like U and V. To each such modes, well, there will be positive frequencies part of the solution. There will be negative frequencies part of the solution. To the positive frequency, you associate A dagger. To negative frequency, you associate A's. And you write the expression. Is this what we did for scalar field? Yes. How do I see that? What is the solution to the scalar field equations of motion? Sorry? Yeah, concord derivative. What is the solution?
Frequency.
Three ways. E to the power of I k mu x mu with what condition? It's not the solution to that. On shell condition. That's it. That's what we did. So we took e to the power of I k omega x with the Dirac delta function. Also, the energy has to be positive, right? We put it in there and we wrote that expression. So most textbooks don't explain to you what they're doing. You just write down that expansion for the field phi. But that is the principle. That is the principle. So now you know how to quantize free fields in arbitrary Kerr space time. You write down the equations of motion. Free fields, the equations are linear. You find the solution. So every positive frequency and negative frequency, if there exists such a notion, you associate creation and annihilation operators. And you find all sorts of bizarre phenomena. Okay, any questions about this? Good. So similar to the scalar field, so the comparison between spinors, as I said, like complex scalar is often discussed because in terms of complexity happen between scalar and fermions, right? We have a similar symmetry here because the action is invariant under global U1 symmetry. It also has the Z2 symmetry, psi going to minus psi, right? There is a charge operator, which is Q dagger, psi dagger, psi integrated over space. And if you could, using the mode expansion, you can write this as the difference between the number operator of B minus D, which means that the charge operator tells you how many particles you have minus how many antiparticles you have, right? Meaning that the particles and antiparticles carry opposite charges. That's what it is. So what do we find? We find that the particle, B particles have positive energy, positive charge. D particle has positive energy, negative charge. And we could construct one particle wave functions, for example, this way. We could construct one particle, one anti-particle wave function. You know all of that. Okay. Any questions? Now you might ask me, if you're ever taken any courses, condensed math courses, you might ask me, well, then what the hell is this sort of this Dirac fermions, this business that people talked about, you know, particles and holes. There was a theory of Dirac back in the days. So what does that do? Turns out that when Dirac was trying to quantize his theory, what he did initially was this. Instead of this annihilation creation operator that I put, what he did was he put both annihilation up. I'm presenting in the modern language. What he did was analogous to putting both annihilation on both creation operators. What happens if you make this transformation? Your Hamiltonian will pick up a minus sign here, and your charge will pick up a plus sign. In this notation, a dagger creates a particle of positive charge but negative energy, right? Up to a minus sign, charge and energy are different. So what he discovered was that he discovered there are two types of particles, particle and antiparticle. They have same charge with opposite energies. That sounds horrible for physics. Why? Positivity of energy is violated, and that's awful. Why is that bad? Stability, right? Because you could lower energy by creating particles, and you're just gonna, it's like a bomb. It's just gonna create pop out particles out of the vacuum, and you're just gonna lower the energy. This seems like a disaster, but then he had a genius idea. He said, what if I'm in a state where all the negative energy states are full? It's a choice, right? When we're talking about the states of harmonic oscillators, right? We picked the state that was killed by all the A's. So we want to say that the number, there are zero particles. He said, all right, I'm going to pick a state where all the antiparticles that I could have ever created are created, because I can only create one of them. These are fermions, right? So I've created every single one of them, So that is my vacuum. The standard vacuum with the sign that I was just discussing, right? Before I talked about the Dirac recipe, was the vacuum of the A particles and D particles. I think I should have this D, because I called them D particles, but they call them B and D. Yeah. So this was my vacuum, but he changed the sign, so he had to change his state in a sense. He said, "Here's my state." Now, there's a phenomenon in field theory, which is pair creation, right? It's allowed. Pair creation creates a particle-antiparticle, right? In his language, this is a phenomenon which is a pair of particle and pole are created. Notice how it's the same physics, right? But using different terminology. And first, it was observed in this way. Turns out that the two formalisms are identical. It's more convenient to talk about positive energies. Preferred to have everything being positive energy. And like you could define normal ordering operators the same way. You're gonna have the number of, then if you normal order the same way, then the Hamiltonian becomes the number of particles plus the number of holes. You run the whole analysis through, everything goes through, then the charge becomes the number of particles minus the number of holes. So what did we learn here? What we learned is that we realized that all along, in quantum mechanics in general, you've been making an implicit assumption, choice of state. It's not enough to talk about AA dagger anti-commutation relations and all that, or define your fields. You are always making a choice of state, vacuum. And you see how the physics depends on it. By making a different choice of vacuum, I could change what I call creation annihilation operators. I could eat the change of what creation annihilation was into a choice of my vacuum. Always, always, always in quantum mechanics, there is the observable algebra or the field algebra. On top of it, there's a choice of state. The choice of state is crucial. This ties in with positivity of energy condition. If your energy is a positive operator, then there is a notion of vacuum, which is the lowest energy, zero energy state, or the lowest energy state, right? If your Hamiltonian is not positive, you want to pick a state, right? Well, you do something like this. But what we want is that we insisted on a theory with a positive Hamiltonian, because all the other sensible theories, up to redefinition of things, turn into any sensible theory must have a stable vacuum. Now, as usual, this is a first course in quantum field theory, so I can make these statements very strongly, but there are a lot of interesting theories that don't have stable vacuum. Yeah. Yeah, of course. There are examples of those theories, but they're not what it is. Well, basically, what it means is that you have to go back to the philosophy of quantum mechanics. What you mean is that you're in a false vacuum. The system is unstable. You pick the wrong state. It's going to decay to some true vacuum. Now, when does that come up in physics? Your state is unstable, but it's metastable. It's going to live there for a very, very long time. And what is a classical example of a unstable? The simplest example of an unstable thing you know, classical.
Spinning top.
Huh?
Spinning top.
This. It's great. Inverted harmonic oscillator. So you could quantize an inverted harmonic oscillator. You could do it. You find instability modes, and if this is flat enough, or then there's sensible physics for short term, so your calculations are reliable, and at some point there's physics that kicks in, so your calculations are not reliable past a certain point. Right? This is a little bit like you have a theory, effective theory, that has a cutoff, meaning that its correlation functions are reliable if you don't evolve them in time for too long. Yeah, we do these kind of things. And as usual, a priori, there is no way for you to know. There's no way for you to know. If your Hamiltonian is not positive, you know that you must have, there is some physics you have missed. All right, I've talked too much. Any questions? Any questions? So now you've seen the charge symmetry. What does the charge symmetry do in the complex boson case? Solves particle antiparticle. What does it do in the fermion case? Solves particle antiparticle. Right? That's what it does, the job of charge symmetry. It's a Z2 symmetry. You could discuss it next to two other Z2 symmetries that came up in representation theory of Lorentz group. Parity and time reversal. Good? Everybody's with me? Parity and time reversal were two Z2 symmetries that came up. This Z2 symmetry, charge symmetry, is another one that you haven't taken seriously. C, P, and T are three symmetries that could be part of your theory, could be symmetric under some of them. Turns out that relativity requires consistency of the theory, requires something like CPT. Well, in even dimension, 3 plus 1 dimensional physics, CPT must be a symmetry. I'm not sure how I'll prove it, but that's a fact. So you can't not violate that. You can't violate that. Lorentz invariance requires it. I haven't explained why, but actually, as a matter of fact, in even dimensions, there's a proof of that. In odd dimensions, there's no proof of that, and it's unclear whether it should be symmetry or not. But there's a full story understood. I did not say that on recording. There's another story that's understood. There's another symmetry called CRT, which is always a symmetry of quantum field in arbitrary dimensions. All right. So what's the R? What's the R? Reflection. What is parity? Take all the spatial directions and send all xi to minus xi, doing nothing to time. What is reflection? Yeah. So you take one of the spatial directions and just multiply them. CRT is always a symmetry of quantum field. So in arbitrary dimensions, there's a proof of that. Yeah, that proof I know back and forth, but we're not going to talk about here. Maybe we will. I'm not sure. There's a shortest path to talk about. This is upper algebras. But all right. So now that we talked about C, it's always good to put it next to R and T. Sorry, P and T, and talk about things. All right. So what is parity? Parity is xi going to x naught xi going to x naught minus xi. So in terms of the fundamental, these were, if you remember, these were the things that were taking us between the different connected pieces of the Lorentz group. So this is what that matrix is in the fundamental representation of the Lorentz group. In the Hilbert space, how does it act? On a scalar field, this is how it acts, right? So you immediately, and then T is like this, minus 1 plus 1, and this is how it acts on a scalar. So you immediately understood something here. When we say scalar field, we're not talking about the representation of SO plus E comma 1. We're talking about representation of O E comma 1. Scalar implies is action, is transformations under the connected piece, which is SO plus E comma 1, and P and T are acting multitude. That's what the scalar is. What if you did something else? You said it's transformed trivially under SO plus D comma 1, but P and T add a minus sign. That's called the pseudo scalar. Right? At any point, pseudo scalar comes up in physics. That's what it is. Because relativity only tells you about, like what representation theory. What we did was representation theory, the restricted Lorentz group, right? You have to make a choice how to transform. There are two. You could have pseudo scalars, you could have scalars. You might ask me, what if you pick different signs for P and T? I'm not gonna answer. But it's a good question. We should look into it. But these are the two things we have: pseudoscalar and scalar. Everyone understands what pseudoscalar is? So how do you tell them apart? Yeah. Time reversal or parity. That's the only way to tell them apart. All right, very good. So now we have these matrices, P mu and T mu. Let's act with them on a vector P mu. How does it transform? Of course, this is the transformation. And T acts this way. These are the matrices that I had above, right? This is that matrix that was 1 minus 1 minus 1, 1 minus 1 minus 1. Sorry. Is it clear what this means? This means that under parity, P naught Hamiltonian is unchanged, but Pi picks up a minus sign. That's what this equation means as an operator. This means that under time reversal, Hamiltonian picks a minus sign, that's P naught, whereas Pi is unchanged as an operator on the Hilbert space. Good? Everybody is with me? So I just said I'm writing them down. So now notice that under parity, Hamiltonian is preserved. Under time reversal, Hamiltonian picks a minus sign. That sounds bad, maybe. Why might that sound bad? No. Like, there's a story you were told before about continuous symmetries, or quantum mechanics. A symmetry was something that commuted with the Hamiltonian, right? These are Z2. So the first equation, PHP equal to Hamiltonian, means PH is equal to HP. So they commute. When you have this equation, it means what? It means TH is minus HT. So it means that they anti-commute. What the hell? Nobody ever told you about that function. All right. But of course, well, then from this equation, it's clear that time evolution is all good. What you want, so here, there was a lie when I said, when people tell you that the charge should commute with Hamiltonian, they're lying. What it should commute with is e to the power of IHT. That's what it should commute with. Now, what happens is that if you pick T to be anti-unitary, it means that H goes to minus H, but IH goes to IH. Here's your example. Remember when we talked about Wigner's theorem, it concluded that symmetries must be represented either as unitary or anti-unitary. Here's an example of an anti-unitary. Time reversal. So a symmetry is something that doesn't, the requirement is not that it commutes with the Hamiltonian, it commutes with time evolution. Because what is a symmetry? The charge has to be invariant under time evolution. All that's required is commuting with the time evolution operator, e to the power of IHT, not commuting with the Hamiltonian. Good? Any questions? For the first time in my life, I finished the lecture with extra time. Unheard of, yeah.
Yes, so you're saying that if it is a symmetrical charge should be invariant in the time evolution, right?
Yeah, what is a symmetry? It means this. It means that dq dt is 0 as an operator equation, right? So this means that, well, what is q of t? Q of t is e to the power of IHT q e to the power of minus IHT, right? If you want this to be equal to q, it means that e to the power of IHT q is equal to q e to the power of IHT. This is the equation. right? To say that H and Q must commute is a leap. This is what Wigner always. Because this equation is satisfied for time reversal. It's an anti-unit. All right, any questions?
Since we have the time, can you go back and talk a little more about Fermion builds up doing observables?
Oh, yeah.
Not entirely sure what that means.
Okay, yeah. It goes back to the philosophy behind that led to the introducing spinners. The idea was that in the Hilbert space, right, what you want is that you want the unitary to act on the vector, right? And what it had to do was that it had to keep the vector fixed up to an overall constant, an overall phase. What happens in the case of Fermion? Let's say you act with the Fermion creation operator, right? On Fermion on the vacuum. So this creates one Fermion. I'm gonna write it, right? So the principle that behind projective representation said take rotation by 2 pi, whatever is the rotation, Ki, J, right? We said that this, well, for when if this was classical physics, rotation, the thing had to come back to itself. We said it comes back to itself, but up to an overall constant, that's unobservable. The overall phase is unobservable. That was the whole principle. We said that the overall phase of the wave function is not observable. That's precisely the philosophy behind it. What does it mean that it's not observable?
There's a probability, so the sun.
Yeah. If you look at something here, the sign and that sign cancel, right? So again, this is not something that some people will get really upset. But what I'm saying is a fact, and what people might get upset over is tradition, right? This is a field, and what is observable are bilinears of it. However, field can have observable consequences in a weird way through interference. The overall phases of vector, nobody complained about that. The overall phase is not observable, yes, right? But through interference, I might be able to cook up observables, right? So here, that's not that context. But what is it? What is this meaning when I say this is not observable? It means that take all the vectors in the Hilbert space and multiply them by minus sign. Nothing about physics will change. But if you take a vector, one vector, flip a sign, and another vector that you don't flip a sign, then you might get interference effects. So this is all right. Now we have time. I can go on and talk about stuff. So is everything okay? So this is a not observed. Side not observed, but it's bilinear observed. Good. We're good. But this
Very good.
Psi x psi y. Now you see the first indication. I'm so glad we have extra time because I can go on a rant. The first appearance of something really interesting. What is this? This is a non-local observable, right? That is not created by multiplying two local observables. It's very, very important, right? So here is the first place where locality, the principle of locality, you're in a sense is a little bit challenged, right? We start with local quantum field theory. Everything is local, right? But there's no guarantee that your observables are all locally generated. They're generated using the fields. Fields are local objects that generate. This should be familiar in a very simple setup. Let's say you have a charge creation operator. In a universe where charge is conserved, you can't possibly create a charge. You can only create them in pairs, right? So our universe, say charge is conserved, putting a charge Q here and a charge minus Q here is kosher. This is an allowed excitation. This is an observable, right? A charge here and minus charge here. But this observable is not created through an operation that creates this guy or that guy. This is a genuinely non-local observable. That's not generated locally using the local algebra of observables. It's the algebra of fields, right? Hopefully this is clear. There should be no process that allows me to create an electron here first, then create a positron. They must always be created at the same time. But there could be non-local. They could spontaneously pop up really far away from each other. Right?
That's the causality is being challenged.
You cannot, it's related to entanglement and all that, but it's not, you're not violating causality. These are correlations. These are 2-point functions. There could be 2-point functions. 1 second. It could be 2-point functions, but it's not a commutator. As a matter of fact, that's a good exercise. Calculate commutators. You'll see that, well, for observables. And you'll see that nothing is violent. Yeah.
But that pair emerges as a singlet state. Must emerge as a singlet state.
Well, the singlet or not has to do with extra stuff, but yeah, sure.
Okay, so they arise entangled.
Yeah, so I'm reluctant to talk about entanglement at this level because there is no the use of the term entangle here is misguided. That you need a new definition of entanglement in the presence of charges. But yeah, I'm reluctant to do that. But yeah. As a matter of fact, here's something. Now, this is an opportunity for me. Spinors have to do with a theory with a Z2 symmetry. Psi going to minus sign. The Z2 symmetry representation, what are the particles of it? They're representations of the Z2 symmetry. What's the representation of Z2 group? +1, -1. That's a representation. Here's +1, -1. That's a representation. Right? Very good. Now, let me stop the recording because I'm gonna go that long. No, let's just keep it. Let's just keep it. All right. So let's say what I want to do. I'm going to talk about operator algebra, right? Let's say I'm very observable oriented, as we all are, because we look around, we see a bunch of things, we cook up a theory, right? I look at all observables I can measure in this room. Patch of space time, right? Now, my friend does the same thing here. The first question is that, are there any observables, if bring together whatever I can observe here and what I can observe here, did we miss any other observables? Were there genuinely non-local observables that we missed? This is the case of a global charge, right? That we miss, if there are global charges. Good. All right. These are two disconnected regions. And the homotopy theory, pi 0, this is not trivial. So for regions that are disconnected, if the theory has new observables, we say it has global charge or a zero form symmetry, because for regions with non-trivial with pi 0, which means disconnect. Pi 0 is the number of disconnect parts. We got new observables. Imagine a region that has non-trivial pi 1, a ring, because there's a loop around this that cannot shrink. If you make a loop by putting together a region like this and a region like this, then you could ask the following. You can measure all observables here. Your friend can measure all observables here. You bring together your measurements, and are you missing any? Are there brand new observables that are neither in here or nor in there? If the answer is yes, your theory has a one-form symmetry. That observable is called Wilson loop, otherwise known as the gauge theory.
Wilson,
Wilson loop. Gauge theory. That's what gauge theories are. You bring in regions that have non-trivial pi 1, and you get brand new observables. That's called one-form symmetry, by the same analogy as zero-form symmetry. What is a D-form symmetry? Take two regions, take regions that have non-trivial pi d, some homotopy group, higher homotopy group, and if you get by bringing, you construct that region from topological trivial regions, you say topological, right? And you get brand new observables, we say that here has D-form symmetry. We're going to come back to this at some point, but I want to summarize it this way. Global charges, gauge theories, all the higher form symmetries, these are setups where the theory has genuinely brand new observables that could not be locally generated. We cook up gauge invariants, all sorts of redundant description to insist on a local description of it at the cost of introducing non-observable fields. So if you ever wonder why do we ever come up with gauge invariant actions where we invent stuff? We engage in invariance. I haven't talked about it at all, but it's a setup where you assume a bunch of fields that transform and there's some redundant description. Why are we doing all of that? Because the theory is genuinely non-local and we insist on a local description. That's what. All right. With that, I'll stop. Thank you. Yes, Wilson loop. I used to teach this, and last year I taught this, but this year I just dropped it. There used to be opportunity. I should be all. No. Uh, Botox. It's coffee and cookies. I'm sorry, man. Oh, really?
Gonna do my best.
I'm sure it will be good.
Yeah.